Related rates is a category of problems that we solve using calculus. And they're called related rates because we are asked to relate the rate of change of one variable to the rate of change of another variable with respect to usually a third variable. And the best thing I can do is just do a bunch of examples so you can get an idea of the similarities between each type of related rates problem. So here's a real basic one. Suppose x and y are both differentiable functions of t and are related by the equation y equals x cubed plus 2x. So we're supposed to find dy dt when x is 1, given that dx dt is 3 when x is 1. So this is the equation that's going to relate x and y to each other. And notice that they are functions of a third variable t. Now every one of these questions is going to ask you something like this. What is the rate of change of one variable, in this case dy dt, when something is happening? Okay, and in this case, actually we know what x is when x is 1, right? Okay, so we're going to take the derivative of this equation with respect to t. So that means we're going to take the derivative of y with respect to t, and we're going to take the derivative of the right side of the equation with respect to t. And what that means is we're going to use implicit differentiation and the chain rule. The derivative of y is dy dt, and the derivative of this is going to be 3x squared plus 2, and then we have to take the derivative of x with respect to t. Okay? And now let's fill in what we know. We're looking for dy dt. We know x is 1, so dy dt will be 3 times 1 squared plus 2, and we know dx dt, that's times 3. Notice I did not plug in any of these numbers until after I had taken the derivative of both sides. So now we just multiply that out. 3 times 1 squared plus 2 is 5, times 3 is 15. So that's how fast y is changing when x is 1. Alright, so that's not real interesting because that doesn't have a real life application, but how about this problem right here? Air is being pumped into a beach ball at the rate of 2.5 cubic feet per minute. So they're always going to give you one of the rates, and in this case they're giving us the rate of change of the volume. And now we're asked to find the rate of change of the radius when the radius is 1 foot. So our key question is, what is dr dt, that's the rate of change of the radius, when r equals 1 foot? Okay, well, the volume of a sphere, we'll assume that this beach ball is spherical, is 4/3 pi r cubed. So we're going to take the derivative of both sides with respect to time, and the 3 will come around and cancel this 3 down here, and I'll get 4 pi r squared, and we have to multiply by the derivative of r with respect to t. So that's what we're looking for right here, is dr dt, right? What is dr dt when r is 1? And we know dv dt, it's 2.5 cubic feet. So let's plug in what we know. 2.5 feet cubed per minute is 4 pi times 1 foot squared, and all of that is multiplied by dr dt. Now take a look at our, let me move this out of the way here. So take a look at our units. I'm going to be dividing feet cubed per minute by feet squared, which will give me feet per minute, which makes sense for the rate of change of a radius. So let's finish this up. I've got 2.5 divided by 4 pi, and our units are going to be feet per minute. And if we bring up our calculator, we'll go 2.5 divided by parentheses 4 pi, and we get about 0.2 feet per minute. Okay, so let's do another problem, okay? Now, this is a classic problem. We've got a house, and a ladder is leaning up against the house. So we'll have a blue ladder here, and it's 12 feet long, and the base of the ladder is sliding away from the wall at a rate of 2 feet per second. So the question is, how fast is the top of the ladder moving when its base is 5 feet from the wall? Alright, so let's call this X because it's horizontal, and we'll call this Y. And so the question is, what is dy dt? How fast is the top of the ladder moving when X is 5 feet? That's our key question. So what do you think would relate X and Y together? Well, I'm looking at this triangle, and it looks like a right triangle, so let's do the Pythagorean theorem. X squared plus Y squared will equal 12 squared. And that will relate X and Y to each other. And I'm going to take the derivative of everything with respect to time. So I'm going to say 2x dx dt plus 2y dy dt equals the derivative of 12 squared. That's a constant, so that's going to be 0. Now I can divide everything by 2 and subtract y dy dt from both sides, and I get that little equation right there. So what do we know? We've taken the derivative. Now it's safe to plug in our numbers. We know that dx dt is 2 feet per second. So I'm going to put that in, and we want to know what is dy dt when the base is 5. So I have 5 times 2 feet per second, and that is positive because it is increasing that distance. Okay, now I don't know y. However, I can find it when x is 5 because y will equal the square root of 144 minus 25, which is the square root of 119. So I'm going to have negative root 119 dy dt. And now I know everything except the piece I'm looking for, which is dy dt. So let's solve for that. So I'm going to get 10 over negative root 119. And let's approximate that with our calculator. So 10 divided by negative square root 119. And it looks like it's about negative 0.92 feet per second. Now it's negative because as x is increasing its distance, y is going to decrease its distance. So that's why the rate of change of y is negative. Okay, last example, and this is a classic. We have a conical water tank of radius 15 feet and height of 30. Okay, so this radius is 15 and this total height is 30. And it's being filled with water at a rate of 5 cubic feet per minute. Well, that is a derivative, right? That's a rate of change. So we can say that the change in volume is 5 cubic feet per minute. So our water is rising as we increase the volume. And as a matter of fact, that's the question. How fast is the water level rising when the water is 6 feet deep? So if I call this R and I call this H, the question is, what is dH dt when H equals 6? Okay, well, the volume of a cone is 1/3 pi r squared h. And we've got a little bit of a problem here because we don't have anything in terms of the rate of change of r. But check this out. If I do this, I have created two similar triangles. The big one is 15 by 30. The little one is r by h. So I can set up a ratio. Whoop, I wrote 15 and I said 30, didn't I? There. So we can say that 15 is to 30 as r is to h. So h over 2 is r. And I can take that, plug it in up there, and now I will have everything in terms of h rather. Which is what I want because I'm looking for dH dt. So we have v is equal to pi over 3 times h cubed over 8, which is pi over 24 h cubed. Now we're ready to take the derivative with respect to time. So dv dt is pi over 8, because the 3 comes around and it cancels a 3 out of that 24. I get pi over 8 h squared dh dt. Okay, well, remember that dv dt is 5 cubic feet per minute. So that goes in right there. And we want to know what is dH dt when h is 6. So we put in 6 for h, and when I square it I get 36. And the only thing I don't know is the thing I'm looking for. So I'm going to get 40 over 36 pi is dH dt. And we'll get our calculator back here. And I'm going to say 40 divided by parentheses 36 pi. Close parentheses. And our answer is about 0.35 feet per minute is how fast h is increasing. So that's pretty much how related rates work. Okay, when you're solving these, I suggest that you write out this equation or this question right here, because every problem is going to ask that kind of question. And don't forget, you cannot plug in any of your constants until after you've taken the derivative. Good luck.